Hello everyone, it's a pleasure to be speaking to you today about the past, present, and future of the domain name system privacy. My name is Nick Feemster, and I am a professor in the computer science department at the University of Chicago. Here's my contact information and my research group's website, and I encourage you to get in touch with me after the presentation or check out our website to learn about more information about our research group. The domain name system is primarily used to translate human-readable names on the internet into machine-usable addresses, specifically IP addresses. DNS's goal is to efficiently locate resources, mapping names to IP addresses. It scales to many users over a large area and also scales well to many updates. The domain name system has many important properties. In particular, domain names have a hierarchical namespace that's divided into zones, and that namespace is distributed over a collection of DNS servers. DNS servers are organized into a hierarchy that include top-level domains like .com, .net, .za, and so forth, and subdomains, each of which have authoritative DNS servers. For example, google.com might have its own authoritative DNS server, or uchicago.edu might also have its own authoritative DNS server. DNS performs the translations between the names and IP addresses, and local DNS servers and client resolvers interact to exchange these queries and responses. DNS achieves many goals. In particular, it's scalable, it can be managed in a decentralized fashion, it's robust, and it has global scope, meaning that each domain name means the same thing everywhere. And a single domain name refers to the same service or website no matter where you are on the internet. Let's take a brief look at how the domain name system operates in terms of resolving queries and where various privacy vulnerabilities come up. When a client wants to resolve a domain name, like www.foo.com, software running on that client server software running on that client called a stub resolver might issue a DNS query to a local recursive resolver. And that local recursive resolver is typically run by an ISP or whoever happens to be running your local network. That local recursive resolver will in turn issue a set of iterative queries to a sequence of authoritative domain name servers for each subdomain within the domain. So first, that local resolver might issue a query to the root server, and that root server might then subsequently issue a referral to .com, and then the query would subsequently be referred to a top-level domain authoritative server that was responsible for resolving .com queries. This procedure would repeat until finally the local recursive resolver was referred to an authoritative server that knows the IP address for www.foo.com. Typically, that would be an authoritative name server for the domain of foo.com. Once the local recursive resolver has that answer, it can subsequently return that IP address to the client stub resolver. Now, because DNS is unencrypted, an attacker or an eavesdropper could simply observe the queries and responses and learn a lot about what a client is doing simply based on those domain names, both the queries and the responses. An oft overlooked but important second point of vulnerability is that the local recursive resolver operator itself can also see those queries and responses. And that's going to become important as we look into various design alternatives to improve the privacy of the domain name system. It's important to note that in both of these cases, or in both of these scenarios or vantage points, DNS is vulnerable to traffic monitoring and so-called fingerprinting attacks that allow an attacker to discover a lot of things about what the client might be up to. What types of things can be learned from DNS? Well, as it turns out, there are a lot of different things that an attacker or an eavesdropper can learn about you simply by observing your DNS traffic. In particular, an eavesdropper might be able to intuit various things about your web browsing behavior, such as the websites or even the web pages that you visit. Additionally, as is shown in this table on the right, an eavesdropper might also be able to determine the devices that you own, or even perhaps your activity on your internet connection at home, which, if you have a lot of connected devices in your home, could be quite revealing. For example, a spike or the existence of DNS traffic from a sleep monitor, a security camera, or a connected refrigerator might tell an eavesdropper a lot about what you might happen to be up to in your house at any particular point in time. Here's an example of an attack on privacy called website fingerprinting that's commonly studied in the context of the Tor network, but is a general attack that any passive eavesdropping adversary can mount on users. An adversary that sees DNS queries and responses from the user can often uniquely determine the website that a user is visiting. And the reason for that is that more than 90% of the Alexa top 1 million websites have at least one unique DNS domain name. And so merely by observing the existence of that unique query, an attacker could intuit or infer that you might be visiting a particular website. In other words, simply observing the DNS queries allows the attacker to uniquely determine the websites that you may be visiting. And it's subsequently been shown that the same kinds of techniques can also be used to reveal the web page that you may be visiting, simply because the set of domain names that a particular web browser might look up on a particular web page may often be unique to that page. It turns out that even using a system like Tor doesn't really help, because Tor itself, in particular the exit relays from the Tor network, also need to run DNS queries. And those DNS exit relays often use a DNS resolving service like Google Public DNS to resolve their queries. We took a look at this in terms of how much DNS traffic was coming from the Tor exit relays to Google Public DNS, and it turned out that almost 40% of the bandwidth off of the Tor network was using the Google Public DNS to resolve its queries, meaning that a lot of the traffic that is coming out of Tor is actually attributable and known by Google, simply by virtue of the fact that they run a public DNS service, and many Tor users actually use Google Public DNS by virtue of the fact that the exit relays they're using rely on Google Public DNS to resolve the DNS queries. There are various approaches to improve DNS privacy. In particular, a lot of these approaches focus on improving data confidentiality and integrity in transit. Recent proposals that we'll talk about involve carrying DNS queries and responses over encrypted transport, such as TLS or HTTPS. And there are various ways to encrypt the transport. To improve the integrity of DNS, there's also a protocol called DNSSEC, which ensures that the DNS records themselves haven't been modified. It's worth noting that DNSSEC does nothing for privacy. It really only addresses various integrity issues with the DNS response records. There are also some efforts to minimize privacy leakage to authoritatives. There's one in particular called DNS QName minimization, which results in the recursive resolver only sending the part of the DNS query to the authoritative that it needs to get an answer from for that particular part of the DNS name. So for example, a query for www.foo.com would only send com to the root server instead of the entire domain name. And the idea there is that every step of the hierarchy or every part of the hierarchy only gets to learn the very next part of the domain name as opposed to the entire domain name. That, of course, really only addresses part of an issue of privacy, which is leakage of the domain name information or the entire domain name query to all of the authoritative servers. Now, importantly also, these existing approaches tend to focus on the adversary that sits in between the stub resolver and the local recursive resolver. They don't tend to address the first hop as the adversary. In other words, what would happen if the local recursive resolver itself was in fact an adversary? In other words, you can encrypt transport between the stub resolver and the local recursive. But if those queries or responses are decrypted at the local recursive and your local recursive is in fact your adversary, then all that encryption really hasn't accomplished anything. Now, ISPs often operate clients' recursive resolvers, allowing them to monitor clients' browsing patterns. But as we'll see, there are an increasing number of parties, including Google, Cloudflare, and many, many others, that have begun to operate these local recursive resolvers. And so there's coming to be an issue of trust in terms of how much one wants to or needs to trust the local recursive resolver with the queries. A strawman proposal to address the threat that might be posed by an adversarial local recursive resolver is simply to change DNS providers and then encrypt the transport between the stub resolver and the third-party recursive using a protocol like DNS over HTTPS, or so-called DOE, or DNS over TLS. Now, of course, this really only just moves the problem, because now you have a third-party recursive resolver, and if that third-party recursive resolver is untrustworthy, then you really haven't gained anything. You've just moved the problem. This has been and is being tried and implemented, and you may in fact be using this technology now without even knowing it. More than 2 years ago, Firefox started testing DNS over HTTPS in its nightly build, and Cloudflare rolled out a public DNS service that claimed to be more private, but then later it was found that Cloudflare was sharing a lot of that query data with other third parties. As I mentioned, you may already be using this without even knowing it. Just this past summer, Mozilla enabled DNS over HTTPS by default for all Firefox users in the United States. You may or may not have seen an alert that looked like this: more secure encrypted DNS lookups, with an obscure message about what that actually means. Now, a typical user might click this away, thinking, sure, more privacy sounds good. But effectively what this does is, in addition to encrypting your DNS queries, it sends all of your DNS queries to Cloudflare. Android has a similar private DNS setting, which, while sometimes not enabled by default, is equally obscure. Who would say no to private DNS? Well, what this doesn't tell you is that enabling private DNS results in all of your DNS queries being sent to Google. Sure, they're encrypted, but do you trust Google with all of your DNS queries? That's certainly a question that's open for debate. Now, the good news is that DNS over HTTPS sometimes performs well. We've done some comparisons both on our local campus network as well as across the United States as part of a larger study in collaboration with the Federal Communications Commission. And DNS over HTTPS outperforms DNS over TLS a lot of times, and often even outperforms unencrypted DNS, particularly in the tail of the distribution. These results are shown for Cloudflare, but we've tested this on Google, Quad9, and several other trusted recursive resolvers and found similar performance. Now, the bad news is that changing DNS providers doesn't solve the privacy problem. As we've discussed, all this does is shift trust from the ISP to the third party. An IP address and domain names are still visible and coupled to the client. And this solution is still vulnerable to monitoring and data requests, particularly at the third-party recursive resolver. So really, we're in an architectural crisis as far as DNS is concerned. It's getting encrypted, but it's also getting more centralized. Modern browsers, and increasingly OSs as we've seen, will select a so-called trusted recursive resolver, often a single trusted recursive resolver by default, and send all DNS queries to that single resolver. So if you trust Google or Cloudflare or whomever with all of your DNS queries, then maybe this doesn't bother you, but otherwise you might be slightly concerned. Now, centralization is not a given. Actually, more than 100 encrypted DNS trusted recursive resolvers exist, and there's a list of them on this website. The question then, of course, is that ultimately we'd like to take advantage of those distributed trusted recursive resolvers, and there's no architecture to date that makes that possible or even really helps us understand how to make use of all these trusted recursive resolvers. And that's part of what our ongoing research is about and part of what I'll tell you about today. Let's first talk about step one, though, which is how to ensure that the local recursive resolver doesn't get to see the client's queries, even if the client is sending queries through that local recursive resolver. Our solution to this is called Oblivious DNS, or ODNS, and there's a publicly available implementation of this, as well as draft standards in the IETF. The goal is to decouple the DNS query in response from the IP address or the stub resolver that issued the query. By obfuscating the DNS query before sending it to the local recursive, generating a referral to an ODNS authoritative server that can decipher the query but not see the original club's stub client IP address. And as I said, that ODNS authoritative server can see the original DNS query since it has the capability of decrypting that query, but it doesn't get to see the IP address of the client that made the request. It only sees the IP address of the local recursive. Here's how that works. So here's our original picture. And what we do is we make a small change by adding what's called an ODNS authoritative server. Now, instead of issuing that query as before, we'll encrypt, the stub resolver will encrypt the subdomain, now the subdomain, www.foo.com, under the .odns top-level domain, using the key of an ODNS authoritative server. That query now is passed to the local recursive resolver, and all the local recursive resolver can see is an opaque name, and then the ODNS top-level domain. That generates a referral to an ODNS authoritative server, which can then decrypt the original query. And note now, the ODNS authoritative server can see the original query, but it can't see the stub resolver IP address. Now that query proceeds as before, just like we talked about. The answer is again encrypted, and the result is returned to the client, who can then decrypt the response. ODNS keys of authoritative servers must be returned to clients, and for that we can use a self-certifying name to exchange the key. So the stub resolver might issue a special query to the ODNS server, and the response comes back with the public key of the authoritative server in a way that's self-certifying, so that the name of that response in fact certifies the key. ODNS servers can be replicated and anycasted, resulting in the selection of the closest ODNS authoritative server. Deploying ODNS requires a couple of changes to both the stub resolver and the authoritative DNS server. the stub resolver needs a way to generate session keys, encrypt the session key with the authoritative's public key so that the stub and the authoritative can establish a session key. Domain names have to be augmented in the way that I've described so that ODNS can be attached as a suffix to the resulting domain name. And the session key itself also has to be exchanged in a way that uses the existing DNS protocols as the transport. Authoritative servers have to be modified to decrypt the session key in the query and then forward the recursive query as before. We have a prototype implementation of ODNS with Go, with the Go DNS library, as I mentioned. There's been some initial progress with Unbound at the IETF hackathons as well. One implementation detail is that the ciphertext of the encrypted query name needs to actually fit in the domain name, in the original domain name or the Q name itself. And sometimes that Q name can be too large. And in these cases, ODNS really just has to fall back and fail. We performed the key there is, of course, that the result should be no worse The important thing there, of course, is that the fallback is simply to just a regular DNS resolution. So it's no worse than not using ODNS in the first place. And that it happens for a very, very small number of queries that happen to have a very large original key name in the first place. Our performance evaluation, which is detailed more in our paper, talks about the overhead of these cryptographic operations, the additional latency for DNS lookups, which really boils down to the additional network latency between your local recursive resolver and the ODNS authoritative server, additional web page load time, as well as the effects of reduced caching at the recursive resolver as a result of the fact that every ODNS stub resolver client is encrypting its queries, and so there's no shared queue names in the cache. There are a number of other practical considerations. In particular, some local recursive resolvers will use an extension to DNS called eDNS0 client subnet that allows an authoritative to figure out where that client is on the internet. This is often very helpful for CDN-based content localization, but it has some privacy implications in that if that client subnet is passed through the ODNS to the ODNS authoritative, then the ODNS authoritative gets to learn the client IP address, and that basically defeats the step of that obfuscation in the first place. The solution here is that the local recursive resolver should strip that eDNS client subnet extension. This has some implications for the ability to localize the client, but again, this is a trade-off between privacy and performance. The other challenge is that the keys are big, and an encrypted query or session key can't necessarily go in the optional record of DNS queries because most resolvers strip the OPT. A near-term solution is to use elliptic curve cryptography and put those keys in the queue name itself. This can be done with a base 64 encoding for the encrypted domain and the key, but it also does prevent the DNS resolvers and the DNS resolvers from using certain extensions. For example, there's an extension called 0x20 encoding that makes it more difficult to poison a local DNS cache. And again, that's no longer possible with because we need those extra bits in the queue name to fit the key. The other thing to consider is that even with all of this, the query type itself, such as is this an A query, a quad A, an NS query, etc., that's in the clear still. There is a solution that came up at the IETF hackathon not long ago that suggested using TXT records and encrypting everything within the TXT record of a DNS query. So that could be a potential solution to that issue. Turns out there are a bunch of recursives that exist that could use ODNS today. Really, the requirements are the recursive resolver can't implement EDNS 0 client subnet, and can't implement 0x20 encoding. And you can see from the green check marks here that a lot of DNS recursive resolvers today do satisfy that constraint. And so there are a number of queries there are a number of open recursive resolvers that we can use to pass ODNS queries through today with absolutely no changes to the existing deployed infrastructure as far as these open recursives are concerned. In summary, ODNS protects privacy by decoupling clients' identities from their queries. Implementation and evaluation show feasibility and low overhead. And ODNS is compatible with existing recursive resolvers and name servers, making it eminently deployable. There's a proposed standard that's been put forward in the ITF, and other organizations, including Apple, have extended ODNS to a protocol called Adaptive DNS that also does not only implements Oblivious DNS, but also does some load balancing of queries across trusted recursive resolvers, which is something that I'll talk about next. Cloudflare is also implementing a version of this called Oblivious DO. Now, step one, of course, was to ensure that the local recursive resolver couldn't see our queries or attribute them to a particular client IP address, rather. But there's still the problem of centralization. We might not want a single local recursive resolver to see all of the client queries for the reasons I mentioned. In particular, it makes fingerprinting a real threat. So the question here is, how do we distribute queries across a larger set of trusted recursive resolvers? Some example ways to do this might be to do a round-robin strategy where the stub resolver picks a bunch of trusted recursive resolvers. Recall that I said there are more than 100 of these deployed. Right? So the queries could be distributed across or through these trusted recursive resolvers so that nobody gets to see everything. Maybe every trusted recursive just gets to see a little. And there are other potential strategies like randomly sending queries to different trusted recursives. And there's another one that we call CDN affinity, which is that recognizing that content delivery networks are serving some of these objects already, so they already know what the client is requesting potentially. And so there's no additional privacy leakage by also sending the DNS query to the same trusted recursive resolver operated by the same CDN. So a bunch of different ways that we can think about how to re-decentralize the DNS. Now, it's unclear what the implications of any of these are for privacy, and we're still trying to basically understand those implications. One way to try to understand those is through an adversary model that relies on website fingerprinting. So recall earlier that I talked about an adversary who could determine web browsing patterns simply by observing the set of DNS queries. And we can test the effectiveness of different distribution strategies by simulating an adversary that can see some subset of the overall DNS queries, running that through a website fingerprinting model such as Flybig's deep fingerprinting model, and seeing whether that adversary is successful at determining which websites a client is visiting. The hope is that some of these distribution strategies make it more difficult for an adversary model that uses the set of DNS queries to fingerprint a website to actually determine what website the client is actually visiting. So we're in the process of studying this now and really working on understanding how these strategies affect client privacy. Now, preliminary results as far as performance is concerned suggests that distributing the queries in a variety of different ways is feasible. Here, what these show is essentially page load time differences for different strategies, the difference between two strategies. So, for example, you can see that the median for all of these is pretty close to 0, meaning that one can distribute queries across a set of trusted recursives in a variety of different ways without too much effect on the overall web page load time. That gives us a lot of latitude to explore different strategies. And the open research question then is thus, which DNS query distribution strategies best preserve privacy? So in summary, I've talked about the past, present, and future of DNS privacy. I've talked about the risks that unencrypted DNS queries pose when you have a passive eavesdropper, either between the stub resolver and the local recursive resolver, or at the local recursive resolver itself. And I talked about two strategies that we're working on to mitigate some of these privacy risks. One called Oblivious DNS, which prevents the local recursive resolver from seeing those queries or coupling them with the client IP address that issued them. And the second strategy, which is a strategy to re-decentralize the DNS across multiple trusted recursive resolvers so that no single trusted recursive gets to see all the client queries. I'll close by saying thank you and showing a beautiful picture of the University of Chicago. And I absolutely will welcome questions. And if anybody wants to follow up, or if anybody is interested in pursuing more research on this topic, I gladly welcome questions, visitors, applications to our PhD program. I'll remind folks that applications to the program are December 15th. That's coming right up. And so if you're interested in pursuing a PhD in the area of internet measurement, internet privacy and security, performance, internet accessibility issues, or in general just the applications of machine learning and other empirical methods to internet privacy, performance, and security, then I would love to talk more. Thanks very much, and it's great to see all of you, and I'm happy to take questions.